SpaceX's new Raptor engine is a methane-fueled full-flow stage combustion cycle engine, and it's so hard to develop. No engine like this has ever flown before. Now this topic can be really intimidating, so in order to bring the Raptor engine into context, we're going to do an overview of a few common types of rocket engine cycles, then compare the Raptor to a few other common rocket engines, like SpaceX's current workhorse, the Merlin, the Space Shuttle's RS-25, the RD-180, Blue Origin's BE-4, and the F-1 engine. Not only is SpaceX using a crazy engine cycle, but they're also going to be using liquid methane as their fuel. Again, something that no orbital rocket has ever used. So we'll also go over the unique characteristics of liquid methane as rocket fuel and see if we can figure out why SpaceX went with methane for the Raptor engine. We'll also break down and explain all the different engine cycle types so that you know what the full flow stage combustion cycle is, how it works, and how it compares to other cycles. So by the end of this video, hopefully we'll have the context to know why the Raptor engine is special, how it compares to other rocket engines, why it's using methane, and hopefully find out if the Raptor engine will be the new king of rocket engines. Let's get started. Rockets are basically just propellants with some skin around them to help keep them in place, and they have a thing on the back that can throw said propellant really fast. And to way oversimplify it even more, the faster you can throw that propellant, the better. The easiest way to do this is by storing all the propellant in your tanks under really high pressure. Then put a valve on the one end of the tank and a propelling nozzle that accelerates the propellant into workable thrust. Types of engine cycles. Now there's actually a lot of cycles here we could talk about, but we are going to stick with the three most common, or at least the three that matter the most when putting the Raptor into context. We have the gas generator cycle, the partial flow stage combustion cycle, and lastly, the full flow stage combustion cycle. The gas generator cycle. This is probably one of the most common types of liquid-fueled rocket engines used on the orbital rockets. It's definitely more complicated than a pressure-fed system, but it's fairly simple, well at least compared to their closed-cycle counterparts. In real life, there are literally dozens of valves, a hive of wires and extra small pipes, helium to back pressure the tanks, fuel flowing through the nozzle, and the combustion chamber to cool it, and an ignition source for the preburner and the combustion chamber. The gas generator cycle works by pumping the fuel and oxidizer into the combustion chamber using a turbo pump. The turbo pump has a few main parts: a mini rocket engine called the preburner, a turbine connected to a shaft, and then a pump or two that push propellant into the combustion chamber. You might hear that the turbo pump is simply called the power back, because it really is what powers the engine. In the open cycle system, the spent propellant from the preburner is simply dumped overboard and does not contribute in any significant thrust. This makes it less efficient since the fuel and oxidizer used to spin the pumps is basically wasted. The closed cycle. The closed cycle or stage combustion cycle increases engine efficiency by using what would normally be lost exhaust and connects it to the combustion chamber to help increase pressure and therefore increase efficiency. With the closed-cycle engine, you don't just use some fuel and some oxidizer and burn that in the preburner to spin the turbine. You actually shoot all the rich propellants through the turbine. So with an oxygen-rich cycle, all the oxygen actually goes through the preburner, and just the right amount of fuel goes to the preburner. You only need enough to give the turbine the right amount of energy to spin the pumps fast enough to get the right pressure for the preburner and the combustion chamber to make the right power to shoot a thing into space, AH. So, the closed cycle improves the overall performance of the engine and is highly advantageous. So how could it get any better than this? The fuel flow stage combustion cycle. Let's move on to the full flow stage combustion cycle, which basically just combines the two closed cycle methods we just talked about. With the full flow stage combustion cycle, you take two preburners, one that runs fuel-rich and one that runs oxygen-rich. The fuel-rich preburner powers the fuel pump and the oxygen-rich preburner powers the LOX. This means the full flow cycle needs to tackle the oxidizer-rich problems, which again is solved by developing very strong metal alloys. However, only 3 engines have demonstrated the full flow stage combustion cycle. In the 60s, the Soviets developed an engine called the RD-270, which never flew, and in the early 2000s, Aerojet and Rocketdyne worked on an integrated powerhead demonstrator called the Integrated Powerhead Demonstrator, which again never made it past the test stand. And the third attempt at developing a full flow stage combustion cycle engine is SpaceX's Raptor engine. That's right, the Raptor engine is only the third attempt at making this crazy type of engine. It's the first ever to do any work and leave the test stand. And fingers crossed, it'll be the first full flow stage combustion cycle engine to reach orbit too. Well, actually, just about everything this engine does will be a first. But all this means SpaceX had to tackle many difficult problems. Not only did they need to solve the same problems with an oxygen-rich cycle, but they also had to precisely control fuel to create the highest chamber pressure of any rocket engine ever, at 270 bar. finally beating the RD-180's record of around 265 bar. And they're not done. They're targeting 300 bar, which is just plain crazy. SpaceX developed their own super alloy in-house that they named SX500. According to Elon, it's capable of over 800 bars of hot, oxygen-rich gas. That may have been one of the biggest hurdles in developing the Raptor engine. Luckily, the fuel-rich side only pumps fuel, so if some hot fuel leaks through the seal on the shaft, it just comes in contact with more fuel. No big deal. Full flow likely wouldn't work with RP1 due to the coking problems with the fuel-rich preburner, but other fuels are still valid to use this design. Since the Raptor can't run a fuel-rich preburner using RP1, you'd think the next most logical choice would be hydrogen. Well, SpaceX didn't opt for either RP1 or hydrogen. They went with liquid methane. Now we finally have another topic to touch. Why did SpaceX choose liquid methane for the Raptor engine? What are the qualities that make it advantageous over hydrogen or RP1? To date, no liquid methane or Methalox engine has gone into orbit, so what qualities does it have that make it desirable? Let's take a look at Methalox and compare Keralox and Hydrolox. Let's put methane in between RP1 and hydrogen. Let's start off with the first biggest factor when designing your first stage, the density of the propellant. Having a denser fuel means the tanks are smaller and lighter for a given mass of fuel. A smaller tank equals a lighter rocket. So here's the density of these three fuels measured in grams per liter. In other words, how much does 1 liter of this stuff weigh? Or really, what's its mass? Starting off with RP1, 1 liter is around 813 grams. RP1 is 11 times denser than hydrogen, which is only 70 grams per liter. And Methalox is right in the middle at 422 grams per liter. It should also be noted that 813 grams per liter are an average for RP1, but SpaceX chills their RP1 in their Falcon 9 and Falcon Heavy for about a 2% to 4% increase in density. But historically, RP1's density is right around that 813 grams per liter. So in the case of density, methane is kind of right in the middle of the others. But there's more than just density. We also need to take into consideration the ratio of how much fuel is burned compared to how much oxidizer is burned. This is the oxidizer to fuel ratio. Rocket engineers have to take into account the mass of the fuel and the corresponding weight of the tanks, so they don't actually burn propellant at the perfect stoichiometric combustion ratio. They find the perfect happy medium that balances tank size with thrust output and specific impulse. Another huge variable of any rocket engine is how efficient it is. This is measured in specific impulse, or ISP, but you can think of this as the fuel economy of a gas-powered car. So a high specific impulse would be similar to that of a high MPG or KMPL. The best way to think of a specific impulse is to imagine you had a 1 kilogram of propellant. For how many seconds can the engine push with 9.81 newtons of force? The longer it can sip on the fuel while still pushing that hard, the higher its specific impulse, and therefore the more work it can do with the same amount of fuel, i.e. its fuel economy. So the higher the specific impulse, the less fuel it takes in order to do the same amount of work, which is a good thing. A fuel-efficient engine is extremely important. And now, due to the molecular weight of each fuel and the energy released when burned, there's a different potential for how quickly the exhaust gas can be expelled out of the nozzle. This means each fuel has a different theoretical specific impulse. Hydrogen is also relatively expensive despite being abundant. Refining it, storing it, and transporting it can be expensive. Methane, on the other hand, is basically the same thing as natural gas and can be relatively cheap. Here's why we get into specifically why SpaceX sees methane as an important or even a necessary part of their company's future. SpaceX's ultimate goals are to develop a system capable of taking humans out to Mars and back over and over. The Mars atmosphere is CO2 rich. Combine that with water mining from the surface and subsurface water on Mars through electrolysis and the Sabatier process, the Martian atmosphere can be made into methane fuel, so you don't have to take all the fuel you need to get home with you. You can make it right there using Mars's resources. This is called in situ resource utilization, or ISRU. Now you might be thinking, well, if there's water, can't you just make hydrogen on the surface of Mars for your fuel? Well, yes, but one of the biggest problems with hydrogen and long-duration missions is the boiling point of hydrogen. It takes serious considerations to maintain hydrogen in a liquid state necessary to be useful as a fuel. So for SpaceX, methane makes a lot of sense. It's fairly dense, meaning that the size of the rockets remains reasonable. It's fairly efficient, it burns clean and makes for a highly reusable engine. It burns relatively cool, helping expand the lifespan of an engine, which again is good for reusability. It's cheap and easy to produce and can be easily produced on the surface of Mars. So let's compare SpaceX's open-cycle Merlin engine that powers their Falcon 9 and Falcon Heavy rockets NPO and Ergomesh's oxygen-rich closed-cycle RD-180 that we see that power the Atlas V rocket, and Rocketdyne's open-cycle F1 engine that power the Saturn V, which all run on RP-1. Then we have SpaceX's full flow-stage combustion cycle Raptor engine that will power their Starship and Super Heavy booster, and Blue Origin's closed-cycle oxygen-rich methane-powered BE-4 engine that will power their New Glenn rocket and ULA's upcoming Vulcan rocket, and Aerojet Rocketdyne's closed-cycle fuel-rich RS-25 engine that power the Space Shuttle and will power the upcoming SLS rocket which runs on hydrogen. So for starters, since the RD-180 and the F1 aren't reusable, their price stays the same. But for the rest of the engines, if we take into account how many flights they will have, now we start to see the RS-25's reusability pay off and close the gap, bringing its potential cost down to just 1,414 KN. But here's where things get crazy. Blue Origin's BE-4 has the potential to be truly game-changing at around 133 KN over 25 flights, which can make it about as cheap to operate as the Merlin at 117 per KN per flight. But if the Raptor engine truly lives up to its hype, it could bring that number all the way down to $20 per KM per flight. Now that is absolutely game-changing. Sure, money and reusability is a 21st century focus for spaceflight, but whatever happened to good old proven reliability? For this, let's first look at how many operational flights each engine has had. The Raptor and BE-4 haven't seen any operational flights, although the Raptor is starting to leave the test stand and being used on test vehicles like the Starhopper. But for now, neither engine has a real flight record. Then we have the F1 engine, which was used on 17 flights. Next up, the Merlin engine, which is at 71 flights, and catching up quickly to the RD-180, which is at 79 flights. But the king out of these engines is the RS-25, which saw 135 flights. Now lastly, how about reliability and service? Between the number of flights and this number, we can get a pretty good sense of how truly reliable an engine is. This number is really hard to just pin down since some engines may have shut down early, but the mission was still successful in a few of these examples. Again, the BE-4 and Raptor haven't flown yet, so these numbers are unavailable. But then we have the Space Shuttle main engine, which is over 99.5% reliable. But that gets hard to define when an engine doesn't fully shut down. We have the Merlin at 99.9% reliable. It helps when you have 10 engines on each flight of the vehicle, and with only one engine ever failing in flight early on in its career, and despite that, the mission was still a success. So it's a very reliable engine. Now to end this, technically the RD-180 and the F1 are 100% reliable, but with the F1 never having any shutdown at all in flight, it gets the bold here, and depending on how you define success and reliability, technically the RD-180 is the only kind of 100% reliable because it got really lucky once. One time it shut down 6 seconds early on the Atlas V mission in 2016 due to a faulty valve. But the mission went on to be a success because of some pure luck with the Centaur upper stage having enough spare Delta V to carry out the mission. Had the valve failed even a second earlier and that mission would have failed. Seeing all these numbers and considerations makes you realize just how many variables go into designing a rocket. It's so crazy to think about how if you tweak one little variable, how many things that can affect. Change any one thing and it can have a massive ripple effect in the design and implementation of the vehicle as a whole. SpaceX's ultimate plan is to make a rapid and fully reusable vehicle capable of sending humans to the moon and Mars as inexpensively and routinely as possible. Not your everyday design goal for a rocket, huh? In order to be rapidly and fully reusable, the engine needs to run clean and require low maintenance with simple turbopump seals and low pre-burner temperatures. A methane-fueled full-flow stage combustion cycle engine sounds like a good fit. For reliability, redundancy, and scale of manufacturing considerations, it makes sense to employ a lot of engines. In order to scale an engine down but maintain a high output, chamber pressure needs to be high. For interplanetary trips, methane makes the most sense because its boiling point makes it usable on long-duration trips to, say, Mars. And guess what? You can produce methane on Mars. So for interplanetary trips, methane-fueled full-flow stage combustion cycle engine sounds like a good fit. Methane is fairly dense, meaning the tank size remains reasonable, which again is good for interplanetary trips, not needing to lug around dead weight, making methane-fueled full-flow stage combustion cycle engine sounds like a good fit. So let's bring it all back around now. Is the Raptor engine really the king of rocket engines? Well, rocket science, like all things, is a complex series of compromises. Is it the most efficient engine? No. Is it the most powerful engine? No. Is it the cheapest engine? Probably not. Is it the most reusable engine? Maybe. But does it do everything really well? Yes. It truly is a Goldilocks engine doing everything it needs to do very, very well. It is the perfect fit for your interplanetary spaceship. And despite its complexity, SpaceX is developing this engine at a rapid pace. Knowing how much tweaking SpaceX did to the Merlin engine over a decade, we're just at the infancy of the Raptor engine. It will only get better and better from here on out, which is crazy. So what do you think? Is it all worth the hassle to develop such a crazy and complex engine? Is this just the beginning for the Raptor engine? And most importantly, is the Raptor engine really the king of rocket engines? Let us know your thoughts in the comments below.